All right, so Huolin Xin in the Physics and Astronomy Department at UCI. Well, this is an old title, remove associate. On the first slide, I want to briefly showcase the data from the Cornell group. So in 2018, they claim they have a new Guinness record on resolution. Now is even better one. This is the electron microscopy image that are showing they're actually resolving a 0.42 angstrom resolution. But we know as electron microscopists or in the optical community, you need to have about 20% contrast to claim you've resolved a spacing on. It's a little bit shy of it, isn't it? Well, this is not to dispute the resolution. They go down to 0.25 now, right? So the thing is, I want to show with the super resolution neural network that we have created, bam, resolution come out, right? And the contrast so vivid and confident, right? What's more interesting is that there's a blob intensity that's actually down here. This is our super resolved image that's overlaid on top of that blob of intensity. Actually, we found a 0.21 angstrom dumbbell that wasn't reported in that paper. But of course, for the expert here is that for blob of intensity that wasn't resolved, you can actually fit infinite number of point spread function to it and still a well fit, right? So take it with a grain of thought, right? So, but however, with those images, you typically know that atomic structures, and you have a lot of prior knowledge you can use. And also you have knowledge about the point spread function. For example, you take one of those. You can actually arrive at this for it to be a most likely solution to this. All right. Okay, so where it can actually help people who are not electron microscopy expert, for example, looking down at spinel cobalt 304, cobalt oxide, manganese oxide. When your resolution a little bit shy of the contrast for resolving the 3 atomic columns, you're kind of wondering what's the structure of this, right? And using my super resolution network, bam, it comes out, all the 3 atomic columns, right? Isn't it fantastic, right? So where the future of electron microscopy, in my shallow view, it would be, of course, everything is going to be robotic, right? Your synthesis of material is going to be robotic. Robotically transfer into TEM. You have automated data acquisition, not only for ex situ experiment that Intel is already doing, but also for in situ experiment, you need to change the stimuli, look at your material, how it changes in real time, right? It has automated data analysis, give you multi-scale information, report the norm, report the heterogeneity, which is super important, right? So this is really, we're criticized for, right? Cherry picking. Right, so this is basically autonomous TM driven by artificial intelligence. This is going to happen in 15, 25 years if we all work together to make it happen, not just relying on the 3 microscope manufacturers. Right, so just to show you how we can actually script the TM to actually do an automated in situ experiment. This is an overnight experiment that was unmanned, right? So this is a piece of a lamella that was cut out from a cathode material. For this audience, I guess you don't really know what it is. But it's NMC A11, and we put down some anchor points. This was heated up to 350 degrees Celsius overnight. So for microscopy, I don't have to really say this thing will drift out of the field of view very quickly. And then basically we need to track the whole piece of material and also go down to these anchor points to take nanoscale atomic resolution images. Here's what you can do. This is a 6-hour heating overnight. No students or me was there. This, look at the scale bars. So we're able to actually track this material as it was moving horrendously overnight. And looking how when you delete this material and you use temperature to actually trigger oxygen loss in the forming of these voids because of lithium oxide vacancies, right? So what's more exciting is now we can automatically take those images at this length scale, which is 100 nanometer by 100 nanometer. To us, this is a large area, isn't this? Because actually for us to get atomic resolution images, we need at least 100 of them, right? So this is something that we really need to break the barrier for, right? So this is where the thing we'll need to address, this is the electron microscopy or any microscopy paradox. We're looking at one small area at a time. How do we actually achieve statistically significant imaging, right? From an entire grid that's 3 millimeter by 3 millimeter all the way down to 1 angstrom, right? So this is really, how do you sample this whole area that's so large and giving you atomic resolution images, right? That's a good question to ask, right? Now, so we show that you can automate the TM to do a lot of workflow, right? And you have the new detectors that can actually give you petabytes of data in a day, right? Well, we know for petabyte data, even reading it through using our workstation will take at least hours, if not days, right? So the human being cannot actually process all of this information when you can take those data, right? So for now, really the solution that can almost replace human being to actually do this, and one of the solutions is the weaker form of artificial intelligence, which is deep learning. All right, so before I go into talk about deep learning, neural networks, I want you to look at this DG3 and appreciate how fast your brain can actually react to it. And telling it's a 3 and there are different types of 3s, our brain have no problem saying, okay, this is a 3, right? Do the classification so instantaneously. It's not an 8, it's not 7, right? So this our brain is actually trained to do this classification. The thing is, when we have this digital image that has 784 pixels, what can we do to actually classify it efficiently and so accurately and so fast, just like our brain, right? Neural network is definitely the solution, right? And how does it work, right? So if you look at this number 9, it has this so-called high-level feature. It has this top circle and the vertical lines. You can imagine that these features are actually stored in these neurons in the second to the last layer, right? Essentially, when you pass 9 through, you have the first and the third neuron that actually light up. And then what will happen is the previous layer is storing these low-level features, right, and breaking down into small segments, right? This is exactly what we want the neural network to do. However, in order to do it, right, this neural network, a really shallow one, not many neurons, it actually contains 13,000 degrees of freedom. These are ways of biases we need to adjust in order for the neural network to do what we wanted to do in the previous picture I showed, right? So here we need to learn. We basically need to train it on a labeled data set so it can find the right weights and the biases, right? So how does it work in the AI industry? Meta, Google, Tesla, what do they do? Right, so this is really the foundation, the ImageNet, right? So Professor Fei-Fei Li, right? When she created this, everyone laughed at her, right? So why do you even waste your time and students' time in doing this, right? The thing is now, right? So look at all of these, right? So you basically have a Google, you have Apple, all of them, Tesla, they have their test cars driving on the street and taking live stream images, and all these images are streamed back to their headquarters, and they have like a humongous group of people just doing labeling all of these images by hand. Okay, that's what they do. And of course now they're doing some computer assisted labeling faster than before. Still, they need humans to actually touch up all of these labeling, particularly for rare events. That's the thing they want to get to train their neural network on, right? So the thing is, what do we need? What do we need for the TM community? We don't have, our data are precious, right? So now we can take petabytes of data, but we don't have enough students to actually label all of them for us. So what we need is a universal data synthesizer with ground truth labels, right? So here are the things that I'm going to talk about. So the first one is a forward model for projection images, right? So you can actually label all the positions of the atoms. A forward model for EELS, for the complete spectra, so you can identify all the edges. And also for near edges, so you can actually partition the oxidation states, decomposition of that. And a forward model for three-dimensional materials. When you really want to get into, a complete library that has all the different kinds of objects that we want to classify. Right? I'm going to briefly talk all of that. So I'm going to skip this slide, right? So forward model for projection images, right? What we're laying down here is, I think most of the experts know, this is a linear imaging model. It's nothing really special, right? The thing is, in order for your images to look like the experimental one, the most important thing is actually put the correct noise into these images, right? So all of these blobs, this is easy, right? It's just a convolution point spread function with your underlying structure, right? And it's really the modeling of these tearing noises for STEM that's really, really important to improve the accuracy and robustness of a neural network, right? And think about other things that you need to model. This is really the noise is the thing that you need to do correctly, right? So with another thing I want to say, right, when the reviewer, I don't know who's sitting here is my reviewer, kept asking me to use multi-slice to create this library. And I was like, I told him, you're crazy. Because, I think Robbie is going to give a talk here in a few days, right? So ask him, right? So this is a silicon dumbbell 211. Right? If you don't focus correctly, and if your point spread function is not coupled to the bonding state correctly, you can promote the anti-bonding excitation. And that will give you a squinted eye effect. Basically, the parent dumbbell distance or location is far from where the actual atomic locations are. So what does it mean? If I were to simulate this image using multi-slice, my ground truths are still where the atomic columns are, which is 0.78 angstroms apart, but this image is going to give me a parent location that's 1.38, right? And that's not going to converge in terms of modeling. That'll give you an incorrect convergence, right? If what you want to do with your neural network is to tell the parent position of the atomic column, do not use multi-slice or any quantum-based simulations.
I totally disagree, but what about just using the projected potentials as your ground truth?
Oh, you can use that, but multi-slice, but typically what people means is you also include your point spread function, like convergence and all of that into
the image, but the output training result is, it could be projected potentials, right?
Well, the projected potential is actually 0.78 angstrom apart, not 1.38. So that's the ground truth. Only if you want to train a network to specifically focusing on deconvolving this image. But if you were to actually create a neural network for general application of any images, what you only want to find is where the location of the parent position is, right? That's not for this specific image, right? You can create the network to actually deconvolve this image to get to the correct solution, right? Correct atomic position. But that's not a general neural network that everyone wants. So what I mean is if you really just want to get a random image and find out where the atomic positions are and the parent position, and do not use multi-slice as your ground truth, as your simulator, please.
Okay. I first want to disagree with you because the multi-slice at least mimics somehow the right diffusion process. That's one thing. So if you exclude that, if you say, okay, I just...
Well, just for the diffusivity, the background, you could just add, you can blur the images with a Lorentzian tail. That will give you exactly the same contrast, whatever contrast you want.
What I want to say is that if you have a neural network, which you prepared with images, in which you don't know there is such a
if you want to formulate a neural network to work on a specific problem, I have no problem you using multi-slice. But if you want it to just tell if the ground truth is the parent atomic positions, then don't use multi-slice.
Let me give you an example. Can I give you an example?
Yes, please.
If you have a network to recognize animals, and you don't give an image of giraffe, you don't know that giraffe exists, and then eventually you observe a giraffe, can this neural network tell you that it is a giraffe? Because you are begging the answer. That is what I'm against. Because you're begging the answer. You say, okay, I need a network that creates something.
So let's back out a little bit. Let's back out a little bit, right? So we are just like the weaker framework artificial intelligence that we're talking here. So our autonomous TM at this stage in the next 10 to 15 years that we want to realize is a weaker form of a human operator, okay? Meaning that if it is told to actually look for dog and cats, it doesn't know what giraffe means. It doesn't have that creativity and transferability. Well, we're waiting for the AI field, the CS people, to actually give us the next generation of the AI that we can actually deploy for these problems. But for now, we're limited to the weaker framework of AI, period. Okay? All right, so let's look at this. So basically, my group has provided this TM ImageNet project and giving you simulated images that almost look like experimental images and give you basically no noise as a ground truth. Segmentation mask, if you are interested in getting the average intensity from these atomic locations, super resolution, background removal, and also all the location of atomic position so you can train a localization network, right?
Quick question. So you were saying that you care about atomic positions of the atoms, right?
Yeah.
That's what you care about.
That's what I care about, period. Apparent position.
Then you don't even need to do simulations. You just use something like Vesta, like even like worse than scattering potentials.
Well, you need to blur it with a reasonable point spread function. That's basically one part of the forward model. The other part of the forward model is getting the correct noise, right? So that's all it needs. That's all it needs, right? So just for the student speaker here, right? When we train it, since the first iteration of the training, it wasn't looking right. This is the ground truth. You have a bigger atom, small atom that are all supposed to look correct. So this is because of incorrect learning rate we used. And of course, if you use a more advanced optimizers and also correct the learning rate, here's the result. So this is on the validation set, and this is segmentation mask, the super resolution processing, and this is a localization. So these models, initial models, we have deployed it to an app and put it on GitHub. Anyone can use it and try. And I think Paul, your student, have tried it, right? And right. So these are validation images, right? It works well on them, right? But the thing is, we really need to test those network is validated on experimental images that have never been trained on, never seen before. I've talked about this being now cobalt oxide before. So this is a lithium titanate. There's a surface rock cell reconstruction. We can pull out the structure really nice, no problem. Structures I have never seen before. This is another one. So this is really where I created this model for, right? So these are the surface atoms. I want to find their location. I want to find out the strain. I want to do quantitative analysis on them, right? So I had a problem using a old method to actually give us segmentation of the surface atoms. But here it achieves that. It's so nice. And here is really the next thing is, what's the precision of the method, right? So here's, we're using Paul, your and group created validation method, right? Silicon dumbbell. And we're able to show that, I'm sorry, I beat your method by 20%. And hopefully everyone can try this and show me that it does. Right? So, of course, you can use it to, since it's so precise, you can use it to extract strain. And for this, this is an image from a piece of lithium nickel oxide where you take lithium out. So here we're interested in the phase transformation, the phase boundary, but also there's one thing, actually, if you stare closely at the original data, you do see there's actually an atom that goes in the tetrahedral sites, and this got pulled out so nicely. We didn't talk about this in this paper, though, just something to show. Here's really, I call it success. When I stare at this molybdenum image, I had trouble knowing where the sulfur atoms are. Or whether there's one sulfur atom or two sulfur atom, right? So this is basically what my neural network gives me. There's very high confidence. You can use this. Again, creating this model, my initial intention is not to give you a very exact location of atomic coordinates as Paul's group did previously. What I wanted to do is just tell you where they are so you can do further analysis on it. You can do whatever Bayesian analysis on it to give you some uncertainty that physicists are really care about. So here, basically, with all of these initial guesses, do whatever Bayesian analysis you want on it, right? So you don't have to get, use your, poor atomic locator to actually work on this so noisy images, right? All right, so of course, you work on time series. Here's a molybdensulfide. You kick the sulfur out and it get tearing apart. You can do so much analysis with this. I'm not going to talk in detail about it, right? So critical thinking, right? So everything I showed so far are just projection images, right? So what can we do in order to actually retrieve this rabbit here, right? So I think Colin is going to talk about tomography in detail, so I'm not going to go through this. It's basically doing a CAT scan in the TEM. You rotate the samples from different angles and reconstruct it digitally, right? So with that, you can actually get information about, for example, these internal Kirkendall channels in projection images you're confused about, whether it's internal voice or actually connect to the surface. And of course, it can couple to the spectroscopy signal, specifically here EELS, to give you a location of different elemental constituents, platinum, iron, right? So now we can easily get down to sub-nanometer resolution. Sub-1 will be what Colin will talk about, and with elemental information, right? So the thing is, right, this elephant with blind man problem is really the electron microscopy paradox that we're facing, right? So all of these age catalysts all look different, right? So one of the things that my group promotes is statistically significant imaging, looking at before cycle, after cycle, and then see how it actually evolved, giving you statistical significant information. And the thing, of course, move one step forward is to using electron energy loss spectroscopy. Here's a iron cobalt with an oxide shell, and the internal is actually metallics, right? This is where EELS is really helpful, right? So basically, for example, from the iron L23 edges, from the L3 that tells you the D hole intensity, and this continuous telling you the composition, right? With these spectroscopy signal, you can actually pull out where the oxidized iron is and cobalt. And back then, when I analyzed this data, I still don't have a neural network that can actually help me partition the oxidation states. I will show you how I would do that now. Next. And of course, one thing that I want to do is to give you time resolution. This is basically similar catalyst that's being in the oxidation process. You heat it up, you put gas in, and see how it actually transforms. Again, this is using electron energy loss spectroscopy. So giving you both information about the composition as well as the oxidation states, electronic structures. Right, so talk about EELS, right? So the thing is, the automation for electron energy loss spectroscopy. So unlike EELS, we all use an EELS. It's so easy to use, right? The software pretty much automated the whole workflow for you for the analysis. The EELS workflow has little automations. So far, it's pretty human operator based. Well, why is that? Is it because Gatang is the monopoly? Just kidding, of course not, right? It's because we're not doing anything, right? So what shall we do? So what's the problem here? Why it has prevented us from doing something similar to EELS, right? So first, low jump ratio. Look at this is EELS. It has all these discrete peaks, so it's really easy to identify peak locations, right? But we're having these edges that can have a very low jump ratio if your sample is thick, right? It doesn't need to be really thick. If 100 nanometer, a silicon L edge is this poor, right? So it's noisy, right? Of course, for EELS, and the other thing is plural scattering affects the jump ratio, and also when we talk about electronic structure, for example, L23 edges. So for some of the reference and calibration free method, you're running into problem because the L2-3 ratio actually changes. How do we actually manage all of this? So we can give you the correct location of the edges, we know where the elements are, and also give you the correct partition and oxidation states. Well, so here we first build an EELS edge net for edge identification.
So when you mean the correct location of the edges, you mean the correct location of the edges knowing a priori what the material is?
Yes, a priori.
But that doesn't...
Not the correct location, correct identification of elemental composition, or what elements are in the spectrum.
What do you train on?
Yeah, well, next. I'm going to talk about, can you give me a few more minutes? Right, so here, again, building a ground truth label, right? So first we digitize, here's how many images we have digitized from the literature, right? And of course, we don't want a noise on it, right? So we use a multi-Gaussian fit to actually create a model for all of these edges, for example, silicon, oxygen, carbon, and all that, right? So on the left are the experimental images, experimental spectra, and we basically smooth it a little bit because we don't want noise in the no noise spectrum period, and we want to add noise later, so we know exactly what the PSNR or whatever the noise it is. And so these are the edges, right? So we have a library for, so these are all the light elements. We're focusing on anything below 1000 eV. And instrumentation broadening, so not just a Gaussian, but also Lorentzian, super important. That's your detector, it's point spec function, don't forget that. And fixed pattern noise, very important. This is where things really confuses me when you have a low jump ratio, right? So I think people who have worked on EELS, and particularly with neon, know this problem, early neons, is that, okay, do I have edges here? I need to move the spectrum around because of the poor fixed pattern noise on the...
I don't want to be a advocate of neon. I don't think the neon is the problem.
No, it's not. The Catan.
It is not that.
Well, it's not Catan.
It's the detectors.
It is the detector. It's a detector, and also we can, how to say...
you will have a hybrid pixelated or a direct electron camera. You do not have that.
Well, so direct electron detector, if the normalization is not done correctly, it could also give you fixed pattern noise. Not as much as this. This is really the optical fiber coupling, and you can't do a correct gain normalization, and never on a dedicated stem. That will give you this problem. And also when your intensity is really low, electrons counts is really low, the fixed pattern noise actually shows up because the normalization cannot be done correctly, right? So we don't know that, right? So. All right, so then with all of these, we put them on the background, right? All the power laws, you just get it within a reasonable range. You don't even need to know the theory, just empirically, and get a lot of data and just find where the range of these backgrounds are. And basically now, I can simulate a spectra that almost look like a real experimental EELS data. And of course, a little bit of expansion, right? So we all know what the EELS problem, right? Give it a little bit of expansion, augmentation, give a little bit of shifts, plus minus 15 eV. So the network becomes very robust when you have these problems in your spectrometer, and also add the fixed pattern noise. So we digitize around 400 core loss edges and covering 20 different elements from journal papers. So with this one, basically these are all the augmentation parameters we have, and also all the jump ratio range we use for these light elements. This is a library of 25,000 spectra with ground truth labels. It definitely can be more, right? So it doesn't have to be 25,000.
Very nice. Just one question. Why are you using Gaussian instead of Poisson noise for the counts?
Well, this is a really important thing for EELS. And in most cases, let's talk about DQE, unless you are using the new DDD, right? And the DQE for our spectrometer, if you can get to 50% with these detectors, you're really lucky. But typically, you're running 30, 40%. So all the later, that reduction in the signal-noise ratio is because of a Gaussian type of noise that's inherent to all the later part of the detection.
Well, it is, but there's very few counts at the really high.
And so this is the thing we can discuss. So let's look at some spectrum. And you will find that the standard deviation of the noise actually doesn't change much with the counts, unless we really get into the regime of DDD. So here I'm creating this primarily for the general electron microscopy who are still using the old instruments. So and another thing is there's a reason the statistician doesn't model Poisson noise. You can't do closed form modeling, and also as we show, if we use Poisson noise, actually this network doesn't converge as well as if we just use Gaussian. And actually we didn't include any noise that's Gaussian and Poisson-like. So what we only include in this network is the fixed pattern noise. So is the fixed pattern noise. That's actually what we included. Okay, for this one. I will show the next one that I do include Poisson noise. Yes.
So whenever I have calibrated the noise in any detector at all, it's always dominated by something that scales as Poisson noise. So including spectrometers.
Right. So for this one, I didn't even include the Gaussian noise. I only included the low frequency noise in the augmentation of the spectra. Okay, and there's a reason for that. The reason being that this network is really deployed for the survey spectrum, just like XPS. I want to survey a spectrum and know where the edges, what edges I have. Okay.
Sorry, one question. Are you sure your Gaussian function capture all the information of your experimental data?
No, I shouldn't. It's as we just talked about. It shouldn't. It should put some Gaussian these.
Oh, I mean the shape of your curve.
Oh, the shape of the curve. That's a multi-Gaussian fit. So we know a Gaussian is not a. Well, it's for statistician, right? So you can write a thesis on multi-Gaussian kernels. Okay.
No, but you want to get quantitative stuff using.
And we know Gaussian kernel is not a complete set, right? You always truncate somewhere, and it can fit things pretty well.
Another thing is for the CCD camera, if you go to very low dose for the case of EELS, it's not important the dark current noise. It's the most dominant term there.
What is the dominant?
Dark current noise.
Dark current noise. That's the fixed pattern noise that we want to include. Well, I understand what you're saying. The dark current noise is actually a Poisson noise. That's because of the readout of your A to D, and that's about 3 to 4 counts of white noise. And okay, moving on. Right. So that's a simple convolutional neural net classification network works, right? So this is a spectral. We want to know where the edges are. Right? So, and the answer should be no, right? It wouldn't, because this simple network only tell you that you have a dog and cat in your images. It's insensitive to where the dog and cats are. So we all know if you want to know where the dog cats are, you need to actually piggyback another localization network part of this component to this, right? So, no. So here's a convolutional network without considering the energy actually failed miserably. And just give you why, like manganese, nickel, cobalt, iron. The L23 edges, they all look like rabbit ears, right? A memory of only spectral features is not sufficient, right? The network needs to know where they are, right? So you need to include the energy axis into this. So basically here, pretty easy, just long short-term memory network will actually work pretty well, right? So here, this is our validation after training, right? So for validation, we'll also compile 400 experimental spectroelectric only for testing, right? So this is basically not just a validation set, but we'll also compiled a new validation set that network has never seen before. So all of the inaccuracy are because of the confusion of the iron and phosphorus, fluorine. And actually, I remember when I was a student, I had a lot of time of being confused by the two. So I'm not surprised that the network can do that. The other thing is a little bit well, surprise to me is the nitrogen and scandium, right? So the reason is that some of the nitrogen near edge we included in the library actually look very like rabbit ears, and they're from the literature. So, so we didn't only include the regular metal nitride, but also some other near edge structures, right? So the thing is, how does it work with different near edges? So these are several different carbon, right? So this one, Peter's not here. This is his real carbon K-edge he put into EMSA abstract. So these are all digitized from the literature. So we can actually predict this carbon really well, regardless of the shape. So we trained it well, right? So, okay, that's the localization of the edges, right? The next is, well, can we do a reference-free and a calibration-free decomposition of oxidation states? Let's use manganese as an example. And the answer is you can. You don't need to exactly know where the energy axis is, and you don't really need to actually find the references. So basically what I did is I digitized almost all manganese data in the literature and left some of them for validation. And of course, this is not a classification, but a regression net, because I want to know whether you have 20% of 2 plus, 30% of 3 plus in it. And here only shape matters for manganese and iron. No memory of energy is actually needed, right? So a rabbit ear is a rabbit ear. Different rabbit ear can be classified by a simple neural network. Plus a regression layer. A forward model that includes plural scattering, right? This is really the thing that's haunting us, right? The L23, the reference-free method or the calibration-free method just doesn't work well and have its thickness effect, right? So we all know. So of course, don't train on everything. Reserve manganese 303 for validation. Okay, so this accuracy is 85%. We can further improve that. Here's our validation. That's on unknown unknowns, right? So the manganese 304 never been trained. So the bulk spectrum is giving you almost 1/2, as theory tells you. And for the nanoscale, manganese 304, there's a little peak here that's actually telling you there's vacancies in the tetrahedral size and a little bit more vacancy in the octahedral side, a little bit more on tetrahedron, right? That's exactly telling you that. So it means our neural network is pretty sensitive, right? And here's sort of validation on all different types of data, XAS, EELS, different energy resolution, and you see for the 2 plus, all of them are not aligned correctly to the correct position. The network has no problem doing the correct participation with a fairly low uncertainty. So I'm really happy about this, right? So we can do this, and this network I would deploy on GitHub and everyone can use it. So I don't think you need to take any references anymore. Just use my network. All right, so further validation. So manganese 304 with different thickness, and you see the ground truth is here. That's the average valence. It starts to tip at thickness T over lambda 1.5 because our augmentation stops at 1, right? That's expected. And for noise, and here's the showing, okay, here the PSNR is in a linear scale, is not in the log scale. So I converted to SNR because that's really showing the drastic effect. So we're doing really well all the way down to a SNR of 2. So they're giving you almost a correct decomposition oxidation state. So we're really happy about this, right? So do I have more time?
Yeah, you've got about another 5 to 7 minutes.
Okay. Going back to 3-dimensional imaging, right? So this is really my dream of doing electron tomography in liquid cell, right? Looking at these dendrites, how they grow, right? So one of the things is that, well, with all these bulky liquid holders, it can only tune to about 20 degrees, plus minus, right? So for, the expert here who are in tomography, right? And it's really this missing wedge of information that's actually limiting me from, preventing me from actually doing this, because it's gonna give me an awful reconstruction that has all the elongation effect and all these tails, all the ghost artifacts. Right, so how can I actually bypass this, right? So before I do that, so for the students, audience, I just want to tell you what it really means by having a missing wedge artifacts. Let's work on this brain teaser, right? So this is kind of a tomography brain teaser. I have a constraint of only the choice that you have, prior knowledge 2, 3, 4, 5, 6, and the sum into 7. This is one projection image you have, and this is another projection into 10 and 11. So I think we can work this out, right? 1 plus 6 is 7, 5 plus 2 is 7, 4 plus 3 is 7. Bingo, we solved it. Okay, but then you realize there's a problem. You can actually swap these two columns. It's still a solution to this problem. What does it mean? The solution is non-unique. You have two solutions to actually choose from. So the fact that our traditional reconstruction algorithm is giving a really poor reconstruction because it's actually picking one solution out of the million possible solutions, and it's a really bad one, right? This problem is can we actually reduce the solution space that we can pick the correct solution, right? There are a lot of things that go into this. Robbie is giving a talk. He's going to talk about his regularizers, right? I'm not going to talk about that. I'm going to talk about how you can actually approach this using deep learning, right? Let's look at different ways of representing tomography data, right? You have an object that's rotating around the axis, right? You take projection images. And the thing is, if you organize it as a function of a rotational angle, you find that it actually sits on a sine curve. Okay, so that's why actually when we actually put those rotation images together as a function of rotation, so it's called a sinogram, right? So essentially when we have a limited Q range, is that the part of the sinogram is actually truncated, right? So the thing is, this is your missing wedge in the sinogram, and if you actually know you have an isolated single object, you can actually fit a sine curve through it and actually in-paint it, right? So this is in-painting problem solved because you have prior knowledge to it. And the thing is, for any reasonably complex cross-sections or objects, you will find that it's non-trivial to actually fill in this missing information here, right? So this is, you can't use any reasonable interpolation to actually fill this information in. What can we do, right? So I want to show this. This is enabled with generative adversarial network. It's called deepfake, right? Transforming Amy Adams' face into Nicolas Cage, right? It does it so vividly, right? Deepfake is so powerful, right? So, but dangerous. But however, GAN, Generative Adversarial Network, solved one of the most difficult in-painting problem in computer vision, right? So we're going to use that. So we basically build our forger, investigator. They compete with the other until it reaches Nash equilibrium. So we have a really well-trained network. And here's the ground truth sinogram. So here's already with the missing wedge. So this is an in-painted sinogram. And you look at it, it actually works pretty well. Let's put it in a real test. This is a reconstruction of this cross-section. So this is the ground truth. This is with missing wedge what it's supposed to look like. This is the in-painted sinogram, and you construct it. Kind of looks good, right? So you have all of these elongation artifacts actually removed. But when I saw this, I was disappointed because I still see some of the ghost artifacts that are actually still present in here, right? But I think, okay, how do we actually solve this, right? So artifact removal is actually another in-painting process you can do, right? So we piggyback another GAN network to it, and actually can clean up this artifact in the sinogram domain so well, right? So this is a two-step in-painting process that actually allow you to in-paint the information in the sinogram domain and then clean up the artifact next. Then we did a little bit more research on what the two networks can do. We find actually only use a network that's the second network in the sinogram, in the tomogram domain, the cleanup network. It actually works pretty well. So we actually just use that to actually in-paint information in the tomogram domain, right? So here is basically a single scale free GAN network that actually can in-paint information, removing artifacts. It works really well. So here's an example. So this is a atomic resolution tomogram of a piece of gold. So you can see here there's a missing information. But after the processing our neural network, not only the missing wedge is actually in-painting, but also the reflection is double. So you have better resolution that's being reconstructed with this. Now we deliver to network, we have infilling process for sinogram and then clean up in the tomogram. And it can actually remove this and just do the artifacts on the tomogram. That works not equally well, actually slightly worse than the first case. But the good thing is that it can be deployed for anyone doing tomography, regardless how you took it, right? Well, your delta angle is 1 degree, 2 degree, 0.5 degree is insensitive to that. It only works in the tomogram domain, right? So what can we do better? Right? So I was inspired by Apple's Deep Fusion, right? You take multiple shots and you merge them together, right? So in our tomography field, we have like gazillion different reconstruction methods and gazillion different regularization you can do, right? So here is basically what we have thinking is, can we actually merge all the different algorithms, only take the good part of it and ditch the poor part of it and actually merge it in the high dimensional space. And actually, yes, it can work. So basically, we'll create a deep fusion network, and we show that only 3 epoch treating already show improved results. We're really excited about this, right? So the thing is, we have the sinogram domain with tomogram domain. We have even more domain that we can actually go into. So can we actually let them work together, right? So we actually create a fairly sophisticated network. Back then, when we did this, it took 2 days to train 1 epoch. So we're like, okay, the hyperparameter training is not going to work for this one. So we ditched it, but now we can actually go back and try it again because the computing power is just so much more than before, right? So, but we actually have a version that's actually slightly light duty than that, which is called a cyclogan, right? So we imagine you have a cat, you have a verbal expression, a kitten wearing a hat, and you can transform it into this, right? That's essentially what the cyclogan does. And what we can do is basically going cycle in the sinogram, tomogram, and sinogram domain, and let this iteration to actually improve this reconstruction. And that is basically what we did, and we find it actually outbeats our deep fusion network. It works really well, right? One step further, can we do something even more fantastic, right? So this is, I was always inspired by AlphaGo, and want to be the Chinese Go master. Similar to this, I'm thinking, can we actually use this, right? So we have many reconstruction method weighted back projection, SARSER, different regularization, iterations, right? Then essentially, when you have a sinogram, you can pick one method or multiple methods with different parameter tuning, give you a bunch of tomogram. And then you can pick to do deep fusion, apply artifact removal, and come back to sinogram, deep fusion upscaling, in-painting, tuning strings of regularization, right? You find what you want to do in the next steps is dependent only on what you get from the previous one, right? This is a Markovian process. It fits exactly the concept of reinforcement learning. So we're actually creating an alpha tomo network to actually do this to further improve our reconstruction. All right, so do I still have time? A little bit. Okay. One of the things that I think I want to talk a little bit more is on
I think you actually have 0 minutes.
0 minutes. Okay, then I'm gonna skip this so and be here. And all models are around, but some are useful. Thank you.
All right.